Hello everyone, welcome to another video. In this video, we're going to talk about an important concept called guessing numbers, and this is going to lead into a very interesting algorithm. So to get started, I want you to think of a number, a positive integer from 1 to 100. And we're going to be thinking of the following questions along with that. We're going to think about what would be the best questions to ask to help you figure out what the number is in under 20 questions. And we're also going to think about, is it possible? And how would this situation change if it was 1 to 1,000? And then we're going to grow this question to the following question. If our list of integers was 1 to n, where n is a large positive value, when would 20 questions be not enough to guess the number? So for us, when we start with 1 to 100 numbers, given that we have 100 numbers to choose from, well, we can have a guaranteed solutions if we were to ask 100 questions. We start from 1, go all the way up to 100, and just ask them if that was any of them was their number. But with 20 questions, if we follow that same strategy, we're only going to cover only a certain specific numbers or certain ranges of numbers. But it is proven that we can ask 2 questions per round and under 20 questions to guess their number, and this is going to be the system that we follow. So we're going to start from the middle and start eliminating where the value cannot exist. So the first question is it 50? And if not, we're going to look at if it's higher or lower. In this case, we're going to ask if it's less than the value that we asked. We're going to know which half to remove. So our very first question, when we're trying to guess the number 42, would work as follows. We're going to ask the first question, is it 50? Then they're going to answer no. Then we're going to ask a second question. This is where we're asking 2 questions per round. We're going to ask, is it less than 50? And they're going to say yeah. That means that we get to eliminate all of these problems or numbers right here, and we get to eliminate those because our number cannot exist beyond the value of 50. So as we go into our next slide, you're going to notice that values from 50 to 100 has been turned off, and we have been given a new midpoint with our new data set starting from 1 to 49, and we asked the question, is it 25? They're going to answer no. We're going to ask, is it less than 25? They're also going to say no. So that means that we can't really find a number that we're looking for within the earlier part of the data set. So we're going to turn all those sections off. And that means that our number can only exist within these activated sections so far. And then with this new set of values, our midpoint is 38. And it's going to say that no, 38 is not 42. So we're going to ask, is it less than 52? In this case, we're going to say no. So we're going to turn off all these numbers within our data set. And we have asked 6 questions so far because we have halved 3 times. At each step, we were asking 2 questions. So at this point, we have turned off 38 to 26. Now our data set goes from 39 to 44. We're going to ask, is it 44? They're going to say no. Is it less than 44? We're going to say yes. That means our number must exist within this range. We get to turn the values of 44 to 49 off, and we get this. It's going to ask, is it 41? And we're going to say no. We're going to say, is it less than 41? We're also going to say no. So we have asked 10 questions so far. And then we get to eliminate all these 3 numbers. And then with 2 numbers remaining, the left value is going to be our midpoint. And it's going to ask, where the algorithm is going to ask, is it 42? And we're going to reply with yes. And the question asked was 12. It took us 12 questions and multiple steps of us having the data set to get to a 42, but we were definitely able to find a number that we were looking for in under 20 questions. And this algorithm comes from a concept called a binary search. What is a binary search? A binary search algorithm is a searching algorithm that finds the position or the index of a target value within a sorted array if it exists. So for example, if we're given a list of 2, 3, 5, 7, 11, has to be sorted. And if we run the binary search function on it, from that list and give it an argument of 7, as in we're looking for that target value of 7, it is going to tell us where that's located, which is index 0, 1, 2, 3. That's where our value or target value is located inside our given collection. So if we were to look at and study the pseudocode of binary search, it would read as follows. Given an array of A of n elements with values records of A naught all the way to A n minus 1, such that every value in our array is sorted. And so a not will be less or equal to the value to the array. And we have a target value that we're looking for, and we continuously look for t unless we can't find it. To do so, we're going to set two variables, L to 0 and R to n minus 1. And this all terminates if L is greater than R. Okay, and we're going to now set another variable called m, which is the middle element, or the position of the middle element, which is going to be, we're going to take L plus R, our left variable and our right variable, we're going to add them all together and divide by 2, and we're going to have the floor of that dictating the midpoint of our location, or midpoint of our data set. All right. Now, if we can find that, well, at that location, if A, our array at index of m is equal to target, then we found that we can return the value of m. However, if anytime a at m is less than t, then we can set the left value to n plus 1 because we don't need to now worry about underneath the index of m. Whereas if a at m is greater than the target, then we're going to set our right variable to n minus 1 because the value that we're looking for cannot exist beyond the right of our index value. So to properly visualize this is our visualization of binary search. We have 10 values, 1, 2, 3, 4, 5, 6, 8, 9, and we're going to be searching for 9. In this case, L's at 1 and 10's at R. R is at 10. Our midpoint is at 5, and it can't exist on the left side of that, so that's all disappears. We generate a new L and M, in this case, so on. 9 is still greater than 7, so we are going to update our L and M again. And this point, when we have removed all the halves and we were able to point our m variable to that value that we're looking for, we were able to search it like so. So binary search, if we were to talk about the big O notation, for time complexity is big O a log of n, whereas space complexity is O of 1, but it uses, variables that doesn't take a lot of storage, but are given a collection. When we are looking for a value within that collection, it would probably require O to the n memory. So the requirements are as follow, though, for us to use a binary search algorithm. The first one is the data must be sortable, and the data set must be sorted for us to use binary search. If we don't have those two criteria, we can't run a binary search. We're better off running a linear search or a searching algorithm. And also, the data within the data set must be comparable to each other, because if we can't compare the values within our data set, then we can't really think about, is this value greater or less than the value that we were comparing our target value to, so that would be very difficult. And lastly, with our pseudocode so far, it will only find a single occurrence of the target, and we would need to write a different algorithm if we were to try to find all the locations of a specific value. So binary search is significantly faster on sorted and larger data sets when we use a linear search on the exact same criteria of a data set as well. So to end this video off, we're going to talk about the relationship between log n and the 100 number values in our data set. Okay, most often when we do think about logarithms in terms of big O notations, we assume that the base of the log is most often 2 because we are splitting the data set into halves continuously. So if we were to do log base 2 to the value of 100, it would equal to a value of 6.64. This means that in 6.64 iterations of us continuously having the data set, we will get to a value of a single value. So it would take about 6.64 halving for us to get to a value of a single one. Okay, so then we know that at each iteration, we were asking 2 questions for us to do the halving, as in, is our number n? If not, is the number less than n? That means that at worst case scenario, if we were to multiply 6.64 by 2, we're asking about 13 questions to determine a number of any number that the person thought of, as long as it was a positive integer from 1 to 100. So then to end off, when would 20 questions not be enough? Well, that means that at log 2 of x would have to equal to 10, as in, since we are doing 10 rounds and each round we're doing 2 questions, we can only do 10 rounds of halving. So if we solve for x, that is going to be our upper threshold of us being able to locate a number with using full 20 questions. And if we know the relationship between powers and logarithm, we will know that the log base of 2 of x, if it equals to 10, then the value of x must equal 1024. The number of 10 represents how many rounds we would need to slice in halves to get to a single number for our value of 1024. The number 10 also represents that in each round we ask 2 questions. Therefore, if we were to do 2 times 10, we were asking 20 questions in total. Therefore, when our data set is bigger than 1024, we cannot get the value that they have guessed under 20 questions. All right, so that is it. That was our explanation on binary search. And reading this pseudocode, I really urge you to try to code this in any of your programming languages that you'd like to use. Anyways, as always, thank you for watching and stay classy.